This lecture is an introduction to the exponential equations. It's basically a review of what you probably learned in 105. As you remember, when exponents were introduced, they were introduced as x squared, or z to the 1/2, or y to the minus 1/5. Notice in these equations, the variable is the base. The x, y, z is the base, but the exponent, well, that was supposed to be a straight line, is the number 2/2 minus 5. In exponential equations, the situation is inverted, so to speak. The number is the base, 2, 3, in this case e. Remember, e is Euler's number, 2.71828, goes on and on and on. It's an irrational number, like pi is. Okay, so here's the number in the base, but the exponent is a variable. The x is in the exponent. Usually we use t, so for example, you might have some function of time equals 100 times 2 to the t over 40. We'll do an equation like that in a minute. Okay, again, the base is a number, in this case 2, and the exponent contains the variable. When you evaluate these exponential equations, there's a certain characteristic pattern depending on the base. So if I have, let's say, f of t equals, just say 2t, okay, and then if I work up this calculation, here's t, and here's 2 to the t. When t is 0, that's 2 to the 0, which is 1, because anything to the 0 power is 1. When it's 1, it's 2 to the 1, which gives you 2. When t is 2, I have 2 squared, 4, up 3, 2 cubed, that's 8, 2 to the 4th, that's 16. So because the base is 2, every time I move by 1 in the exponent, I double the amount that I have. I double from the previous answer. 1 becomes 2, 2 becomes 4, 4 times 2 is 8, 8 times 2 is 16. That's because the base is 2. Now the base could be, for example, 3. So if we have the same calculation here, this is 3 to the t, 0, 3 to the 0 is 1. 1 would be 3 to the 1, which is 3, of course. 2, 3 squared, 9. 3 cubed is 27, and you can see what's happening here. Every time I move by 1 in the exponent, it triples. The value of the function triples. That's because there's a 3. I can also go the other way with negative values of t. So minus 1 would be 2 to the minus 1, which would be 1/2. Minus 2, 2 to the minus 2, which is 1 over 2 squared, that's 1/4, and that continues going on like that. In this case, again, it's what it is dividing by 2 now. Same here, you would have minus 1, that would give you 3 to the minus 1, which is 1/3. Minus 2 would be 3 to the minus 2, and that's 1/9, and that's continuing, dividing by 3. Here are the graphs of those equations. This is 2 to the x, and here's 3 to the x. Remember, when x was 0, they had the value 1. This is a common spot on all these functions of this form. As t increases, I guess that's x in this case, as x increases, then when we have 2 to the x, we have doubling. So from 1 to 2, 2 to 4, and then we've got 8 when x is 3. For 3 to the x, it of course is growing faster. When x is 1, it's already up here at 3, then it's at 9, and then it's off this chart there at 27. So you can see this trend, and it does hold. The bigger the exponent, the faster it grows. And now when we go the other way, though, at minus 1, the t would be at 1/2, but 3 to the, I'm saying t, 3 to the x would be at 1/3. So at this point, 2 to the x would be 1/4, whereas 3 to the x would be 1/9. So for a bigger base, it grows faster and it decays away faster. That's why you see the red line here at the bottom for the growth phase, but here in the decaying phase you see the red line on top. E, Euler's number, is 2.71828. It's between 2 and 3 and closer to 3, so you can just see that graph of it right in there. And also, of course, when x is 0, e to the 0 is 1. The way I've drawn it here, these are growth equations, and generally we pay attention to this side and call that growth equation. Okay, I'm going to erase this board now. Okay, so with everything in this form, these are growth equations, exponential growth equations. Here, here, and of course here as well. But on this side, you can see it's decaying away, but if we have something that's decaying exponentially, instead of using this part of the graph, we just rotate the graph about the y-axis. And then we will get what happened to, whoops, it's supposed to go through here, and it decays away. Hardly drying, good. Okay. And it comes up here and decays away. At any rate, that was pretty bad. They all go through this point, so we'll make it go through that point. Okay, I'm going to edit that out. These are your growth equations right here, and you can see that as x gets bigger, they get bigger. So that's your growth. You could also take these equations, or this expression, and rotate it about the y-axis. And these would look like, they would come down here, I don't know why I seem to always miss that, and decay away. Alright, I want to draw that freehand just to show you how it works, but it didn't work that time either. These are your growth equations. You can see over here, this looks like decay. And to capture that, we write the equations differently. Instead of 2 to the x, we write 2 to the minus x. Instead of 3 to the x, we write 3 to the minus x. And then we get these decay equations. The effect will be that this graph is rotated about the y-axis. So what was over here goes over there. And this side will be decaying away. Of course, over here, it would look like a growth equation. And this might be 3 to the minus x. Again, this is growth. This is decay. And the equation is written with a negative sign. 3 to the minus x, 2 to the minus x, e to the minus x. So we'll study some exponential growth first. This is the general form of any exponential equation for, not for radioactive material, but for something like bacteria, and it's for growth. Okay, I got copy and pasted there, was wrong. Okay, let me write that bigger letters here, a to the 0 times 2 to the t over d. That's the general form. A0 is the amount you have at time t equals 0. That's your initial amount. The d is called the doubling time. It's the amount of time it takes in order to double from the previous time step. So if it's typical bacteria, it could double in 20 minutes. But here's an example where we started with 100. Say we started with 100 bacteria, and this bacteria has a doubling time of 40 minutes. Before, when we just had 2 to the t, we saw a pattern that every time the t moved by 1, we doubled. In this case, if we moved by 1, we would not see the pattern. Instead, we move by whatever is in the d, the doubling time. So we're going to move by 40 minutes. We're going to go from 0 to 40 minutes, then to 80 minutes, and then to 120 minutes, then to 160, and then to 200 minutes. So we're going to count by 40s. We count by this d. And there's a lecture on time constants that talks about this specifically. But let's put these in the equation. So if we put a 0 here, then we would have 100 to the 1, which is 100. And we said that was our starting amount, and it is our starting amount. You can see here at t equals 0, we get 100. 40, put a 40 into the equation. 40 over 40 is 1. 2 to the 1 is 2, so we have 200. So we doubled. In 40 minutes, we doubled. Let's go another 40 minutes to 80 minutes. Put the 80 here in the exponent. That becomes 2 squared, which is 4. So now we have doubled again. And this pattern continues. Here's a graph. Here was our initial equation, but the a was 100. So this is really a graph of the following equation: 100 times 2 to the t over 40. You see, once you've moved 40 minutes here, 40 whatevers, then you've doubled. Move another 40 minutes, and you've doubled again. Move 120, that's another 40 minutes from the 80, and you double again. And the pattern continues. Here's radioactive decay. Like I said earlier, it's the same equation except with a negative sign. This is the equation for radioactive decay, or anything that decays by halves. That's t over h. Now h is not doubling time, it's called the half-life. Often it's written t with a little 1/2, but it's hard to write that with clarity on these slides. So I used h. Again, this term is the initial amount that you have. So say you start with 100 and you have a half-life of 40 years. So we're doing the same problem, the same numbers, but now we're doing decay. So when we substitute these numbers in, when t is 0, we get 100 as stated. Now we move by 40. In the previous equation, we moved by doubling time. Now we're going to move by half-lives. So it's 40. We get minus 40 over 40 in the numerator, or in the exponent, which is minus 1. As 100 times a half. Now we've decreased to 50, decreased by half. Move another 40 minutes to 80. 80 goes in the denominator. That becomes 2 to the minus 2, which is 1/4. And we dropped by another half to 25, and that pattern continues. Here's a graph of that equation. We start with 100, and we have a half-life of 40. So in 40 minutes, we're down here. That's called just a half-life. It's also called the time constant. So in 40 minutes, we've dropped from 100 down to 50. We have only half the material left. We go another 40 minutes, and the 50 drops by half to 25. So that's all we've lost, well, 3/4 of the material by now. So we won't go from 25 down to 12.5 in another 40 minutes, and the pattern continues. So this is your radioactive decay. And here again is the equation. It's A equals A naught times 2 to the minus t over the half-life. That's the decay. For the growth, it's the same equation, but in the exponent, there's no negative sign. So here's your growth. Here's decay. Just like to make another comment about exponentials. An exponential grows faster than any polynomial. I'll write it down. It will catch up to any polynomial and then exceed it. And the linear equation, of course, is a polynomial. Just a polynomial of degree 1. Okay, so that's a big statement for this slide. And what I'm showing here is what's called Malthusian Catastrophe. Thomas Malthus observed that population seemed to grow exponentially, but that agriculture only grew linearly. And the mathematics is correct. If I start, it's hard to see what I started with there. So you start with some population and your agriculture is feeding that population and some more. So you have more agriculture than you need. Of course, you could export some. But as time goes on, that population growing exponentially eventually is equal to the agricultural linear growth. It doesn't matter how steep that is, eventually the exponential population will overtake it. And then there will be a catastrophe, that's a Malthusian catastrophe, and after that there's starvation because you can't even feed the people of your own country. This isn't true in the quote-unquote real world, although the math is correct. It's not true in the real world because agriculture has grown by leaps and bounds and wasn't constrained to grow linearly. Also, populations don't always increase. Many populations of the world, in fact, are decreasing. I think Germany has a negative population rate. England, it's about flat. And Russia, I think it's negative population growth. So his assumptions weren't true, but his math was correct.